But so sorry for losing the time. Okay, now the couple of things. Let me just. One thing is, Prof. Dinesh, I would like to postpone tomorrow's lecture.
Okay.
What I want to do, because I have to just rehash my slides. I was running into some changes. I thought I would revise
that
them.
works well for us also, because tomorrow is a holiday for us. And
I see. That's good.
Exam.
Oh, I think Monday
conduct
also.
a comprehensive exam at the same time. So,
all right.
It's actually
so Monday
also, this guys.
So Monday also I'll escape, and Thursday, Friday I would have.
Okay, perfect. Yeah.
And what I'll do, I
you
found
need only 2 more sessions.
I think so. 2 more lectures, or maybe
Okay.
I'll see.
Okay.
Another thing is,
so
today
that will
I
be on the
said
21st and 22nd, Thursday and
yes,
Friday.
that's right. And another thing is, I said bolted joint I left last time, when I was talking about the design guidance.
Yeah.
But I felt later on, I realized it's getting too wordy, basically, which is, so I'm going to convert each of those recommendations into pictorial form.
Okay.
So, just to make it more clear, otherwise it becomes confusing. So I thought I'll put the diagram for each of the recommendation and the diagram, so it makes sense. It doesn't confuse. So I myself got confused when I was again doing it. I've been doing that, but I thought now it's better to put them in pictorial form, each one, so it makes it very clear. Okay, so I'll not continue with the bolted joint today. I'll start notches.
Okay, sounds good. Yeah.
So let me open my file now.
So it's already been uploaded to the Teams as well.
Yeah, that's good. So holes and notches. I see Bengalūrū. Okay, now let me go to the team. Where did team icon gone? Team icon.
You're probably connected from a browser, right? Not from the Teams app.
So I can't see on the bottom that team browser icon. Where do we go? Oh, here. I could see something. Getting started. Not now. Where I am? My God, it's causing a. Okay, so it's on Google. Sorry, I was going into the screen share. Okay. Now, can you see my screen now?
Yes, we can. Yeah,
that's
please
good.
Go ahead.
Okay, so we have lost the time. Sorry for that now. But as I said, I will continue the bolted joint next week, changing some of the slides. And so today I'll start with the analysis of holes and notches in composite. Now, this is part of the damage tolerance philosophy. Yeah. So I had all.
I can't see the slide anymore.
Oh, is it?
Yeah.
What happened?
Can anybody else see the slide?
No, sir.
Okay, so desktop window, share. Now, let's see.
Yeah, this is perfect. You can make it full screen.
Can you see now?
Yes, we can. Yeah.
Okay. So now this analysis of holes and notches, which I'll be talking today, is a part of the damage tolerance philosophy. Now, most of the things in damage tolerance I had done during the certification, but I would be showing some slides next time for damage tolerance and some durability work. But before that, I thought, let me give you some background about the notches and holes analysis, which is very important. Although I'll not be able to go all the methods in detail, but I'll just provide you some empirical approaches which are useful to begin with. Okay, just disclaimer, don't worry. So contents are effect of holes on strength, effect of notches on strength, and empirical methods to predict notch strength. As an introduction, so the presentation discusses some empirical analysis methods to analyze the sharp notches or holes in fiber reinforced composite laminate structures. We are not talking about the metals in this presentation. It is only limited to the composites. The loading is considered only in one direction for the analysis, so it's a limitation of these methods. Multi-directional loading requires generally finite element complex variable methods to determine stress or strain fields. The analysis methods are limited to holes and notches in unstiffened panels, and method present are limited only to initiation of fracture and doesn't discuss the damage propagation. So this is just a brief background, what is coming ahead on these slides. Some of the references are listed, but that's not the whole end of the references. There are many other references which I might have used in my presentation, which might have not been included. But some of the important references are already there, like say, this is a good report by Madhukar and Overbook. They wrote a review, which was very comprehensive review about the notch and hole analysis published almost 40 years back. Good work. Then this work is from the NASA. So that's also very good work done by NASA, Mr. Rhodes, Mikulas, McGowan, the big team over there. Newsman and Whitney is the reference, which is very useful. The reason being, I will be talking mainly about the point stress criteria in the discussion for the notch strength estimate, which is very popular and which was given by Newsman and Whitney. Newsman was a master's student at the time with Whitney, and they published in 1973-74. They did this work and published this point stress criteria. Another publication by Whitney Newsman, then Siegel like us, and I have some of my publications from where I pulled out some of the slides. Poe has done a lot of work, and you can find some of the fraction mechanics approaches in this report and lots of other reports from NASA website. Wadhub Seisenman, in fact, initially they started with this work, which I have removed that actually, some of the work which they had done from the slides over here because too many methods were there, so I removed, but I'll explain you some genesis of that. Broix, probably the fraction mechanics book, which is classical reference. Okay, some of the issues, the various damages in the composite, there are various types of damages, which I have not listed everything. Normally holes, normally you won't have in practice a clean hole like what I've shown. On the structure, there will be jagged hole, damaged holes, the notches and slates, that is sharp notch, impact damages. You may have delaminations, you may have scratches, and some other damage types, which I will be just touching over here. The main thing is once again, only the unidirectional loading, multidirectional loading is difficult. So I'll be just discussing the limitations of the methods. Now, the issue is, if there is a damage in the structure, the damage does reduce the residual strength of the structure, depending upon the size of the damage. As you can see, qualitatively, as the size increases, the residual strength also will decrease. Although here, this is showing like asymptotic, this is percentage, this is damage size with respect to the panel size. Suppose panel becomes very large, then the residual strength. For the holes, of course, it approaches asymptotic, but for the crack, it will keep on going down, which we'll just show later on. Okay, issues for the damages in structures is there are irregular damage shapes, idealization shape. So what happens when you want to analyze, it's very difficult to analyze irregular shapes. So you will have to approximate with some kind of a regular damage shape for the analysis. Then prediction of residual strength. The methods are very much limited in their applicability, which we'll discuss. The prediction of fatigue behavior, extremely difficult in the composites. Prediction of damage growth, extremely difficult in composites by using any of the methods available. Effect of materials and structural details on static and fatigue strength and various parameters. So damage analysis, damages analysis, circular holes, sharp notches. That's what we'll be considering now. In this slide, what we are trying to show, the reason why we are considering this is stress distribution ahead of the hole. In order to consider the effect of the hole on the residual strength, we use the stress distribution around the hole. Of course, this is only for a unidirectional loading, and for multidirectional loading, we do not have any analytical expression available in a closed form. And that's a difficulty. We can analyze the unidirectional loading easily, but not multi-axial loadings. So here, what you see, Sy is the stress distribution ahead of the hole edge. And this is given by this, a function of R, and the distance from the edge of the hole is X. Okay, now if it's isotropic material, you would consider isotropic material, KT is 3. So if you put here 3, so this is nothing but an expression for the isotropic material. KT is a function of an isotropy of the material, which is given by this equation. And E by EX is nothing but in Y direction E, X direction E, and nu YX Poisson's ratio, and this is shear modulus. So this is elastic Young's modulus, longitudinal modulus. This is transverse modulus, shear modulus, and Poisson's ratio. So this is just expression. We need this expression in order to derive our residual strength criteria. Okay. This graph is only showing the effect, plotting the stress distribution, which I showed in the previous slide, as a function of the diameter or the radius of the hole and position along the X for the stress. Now, what this diagram tells us, when the hole is of a smaller diameter, like 3 millimeters, say, this is 10 millimeter and this is 40 millimeter. And what you are seeing, the stress distribution ahead the hole changes depending upon the diameter of the hole. Even though the stress constant factor, that is SYSG, this is for quasi-isotropic, that's why here this is terminating at 3, because for a quasi-isotropic, stress constant factor KT is 3. If it's anisotropic, significantly anisotropic, KT could be 4 or even 5. So what you are seeing here, if you have a larger diameter of hole, then larger portion ahead of the hole edge is under high stress. So this is higher stress compared to the smaller hole. What you're seeing, this is why I've said, okay, high stress zone, because this region is of a high stress here. But the stress gradient is very sharp for the smaller holes. So for small holes, the stress drops very rapidly from the edge of the hull compared to the larger hole. Okay, notch sensitivity in composites. So notch sensitivity because the laminate or the material is sensitive to the notch, and the notch sensitivity depends upon the layup, material loading, notch size and shape, local damage developed to the crack tip at the hole edge, and KT varies with anisotropy. I've just shown, based on this equation, which is there, this KT infinity, try to give you an idea how the KT, which is 3 for the isotropic material, as you can see here. This is the 3 value for isotropic or quasi-isotropic material. But as the anisotropy increases, as you can see, the KT can reach to almost 7. What we mean by anisotropy, percentage of 0-degree fibers along the load direction keep on increasing for a layup. So if you have a unidirectional layup, say, where 100%, that is a tape laminate, 100% zeros, and if you drill a hole in it, try to load it, you will find the anisotropy. Due to this, the stress constant factor is 7 almost. Whereas if you have 0% is 0, 0% is zeros, then, or say, suppose you have 45 laminate only, plus minus 45, you will find the stress constant factor of 2. So there's significant variation depending upon the type of the layup we have on the stress constant factor. It doesn't happen with the isotropic material. Isotropic material is always 3. And this behavior has the implication on the failure or residual strength of the composite materials compared to the isotropic materials. Next is the stress distribution for the crack. Similarly, we have SG. SG is a gross stress. So I have written here SY, X0, at X, 0 is Y, Y equal to 0, is equal to X upon root X square minus C square. This is from fracture mechanics considerations. Now, what you would notice, this functionality for stress distribution is not dependent upon anisotropy. There's no anisotropy term appearing in this, whether it's isotropic or anisotropic, the behavior seems to be same as far as the stress distribution is concerned. Okay, now I've just plotted the stress distribution for the cracks. As you can see here, if you have a smaller crack, 2C equal to 5, then you find the maximum stress at the crack tip, near the crack tip. Of course, right at the crack tip, theoretically, you will find if I have X equal to C, right at this edge, the stress becomes infinite. That's a stress singularity, theoretically, from the fracture mechanics. So here, of course, we have not gone to X equal to 0 because that will be approaching to infinity. But what you can see, just away from the crack tip, the stress keeps on increasing as you increase the size of the crack. Whereas we saw for the whole edge, right over here, X equal to 0, right? So here, x minus c equal to 0, the value sy upon sg does not change. It remains same. Like for quasi-isotropic or isotropic is 3, whereas for the crack, it is different value. Here I compared the stress distribution for the crack and a hole just to illustrate the difference in the stress distributions. Now, here if you see dotted line, this is for hole diameter of 5 millimeter and crack also of the same size, 2c equal to 5. And what you see here, the stress distribution for the hole and the crack is very close to each other if the crack and holes are small. But if crack increases in size, like 2c equal to 40 millimeter, long crack, and hole is also 40 millimeter diameter, what you are seeing from this stress distribution is that this is for quasi-isotropic psi. Hole stress, because here it has to be the same as we have seen in the previous graphs for the hole. And then you have some gradient here. But for the crack, this stress keeps on increasing significantly. And in this region, very high stress. What this tells us, naturally, if you look into this stress distribution, it will tell us that 40 millimeter hole doesn't seem to be as critical as the 40 millimeter crack here. Whereas 5 millimeter crack and 5 millimeter hole might land up into the same residual strength. So that will be the difference between the crack and the hole. For the small cracks and holes like 1/4 inch or 6.4 millimeter hole, virtually you will find the residual strength would be same. But for a larger hole and larger cracks, the stress residual strength will deviate significantly because of this phenomena, as you can see from here. Okay, so this is just description. I won't go into the details of this slide. I just tried to show the qualitatively what happens here, because this is important to understand all the empirical relations which have come up to predict the residual strength of a hole or a crack are based on this phenomena, what we are showing here. This is similar to the plasticity in metallic materials. So as we start loading the laminate, at smaller loads, some kind of a small damages start. Initially, what will happen, the 90-degree fibers or 90-degree fibers layer. So matrix will start cracking, transfers to the load direction. It is 90-degree plies. Right near the notch or the hole tip, because there are high stresses. So naturally, when the stresses are high, it will lead to the damage initiation. So first damage will be matrix cracking. And then the damage size will keep on increasing, matrix cracking, fiber splitting, some kind of a delamination, all sorts of damages could occur depending upon the layer. And then you would find significant amount of damage, and finally the fracture would occur. Now, if you compare this type with a metal also, similar thing will happen, because right at the edge of the hole or the crack tip, there would be higher stresses. So material starts yielding, and the yielding will spread across the net section, which will relieve the stress concentration and provide you the final failure, which would be much higher stress compared to 3 sigma value in isotropic material. Same thing happens in composites. This phenomena does relieve the stress concentration factor. For the smaller hulls, the effect is more, and that is why the residual strength is higher than considering KT sigma. Similarly, for the crack, I have tried to show similar pictures over here. This I have taken the work from the work of C.C. Poe, Christopher Poe from NASA. I just read on the picture. So what you are seeing here, this is a low displacement curve, and essentially this is showing just qualitatively the damages which are growing like this one when you have a crack. So similar thing to the whole edge, the damage will keep on growing. And actually, I'm showing some pictures, actual picture, which are from my papers, which I had done at NASA while investigating the fracture damage propagations later on. You can see here, say, these are compact M. This is central crack coupon. And you can see this one is a compact tension coupon, which I'd use all sorts of coupons, in fact, to investigate the fracture behavior. And this, the layup for this one is plus minus 45. So when we started loading, you can see here, this is the original crack right tip. And then there's a matrix crack. That is 45-degree ply cracking, and another 45, the other side will be cracking. And you find lots of the damages. Now, if it is a metal, you would find the crack will propagate along the same plane as the initial crack in the same direction. But in the composite, the damage doesn't propagate in the same direction unless it's a unidirectional coupon and you're loading at 90 degree. Then the crack will be like a delamination. Otherwise, you would never find self. So we call that self-similar if it's a propagating in the same direction. If it's not, this is non-self-similar. So this is non-self-similar. Similarly, this is quasi-isotropic laminate. As you can see, at smaller loads, the damage is starting, and that near the fracture, much larger damage has occurred. So this is virtually we can call like a self-similar crack growth. Crack is growing, although there's a lot of damage away from the crack plane. Another one, this should be 0.90. Now, this is a bad layup. In practice, you would never use it. It's terrible because it will lead to delamination. As you can see here, that in the loaded hull, near the loading hull only, the plies have delaminated. So what I had seen at that time, I didn't realize that this is pretty bad, which I would never design like this, of course. But this gave me a good feel. I found that at this interface, it just delaminated into 2 parts. Clean delamination, virtually split. And I was talking about interlaminar stresses, and this is due to the interlaminar stresses. Very high interlaminar stress will exist because you are clubbing or bunching of the 0-degree ply and 90-degree plies. So you'll create a very high interlaminar stresses, which is causing the delamination, as you can see here. It's a true thing, and you can see the effect of high interlaminar stresses, bunching of the plies together. So it's a good phenomena which are observed. But you see on the left, this is 0 to 92 laminate. Even 0 to 92 had the similar thing here. It's to that less extent, but there's always a risk of delamination. Now, these are terrible layups. I would never use it in practice. Similar pictures, others, damage propagations. So now this is not my work. This is from NASA, Christopher Poe's work, where I just take in to demonstrate. Suppose you have a 0 unidirectional layup, then what happens? You will expect this is the original crack. And when you are loading this, then you would find that crack cannot propagate this way. There are fibers. So it has to break the fibers. The simplest path is because there is a shear stress existing over here right near the crack tip. And this shear stress causes the split. So the crack will propagate along the load line. This is a load line along this one. And as you can see, crack propagating along the load line. So I also experienced in one of my studies the unidirectional laminate that it just split into 3 parts. This is separate, this is separated. So 1, 2, 3. Clean. 0 to 90S layup. Also because there are higher number of zeros. So you find even though there's 190 layer, still the crack is propagating along the load line. So why I wanted to just show you the effect we call in our study the self-similar crack growth and non-self-similar crack growth. If the crack propagates along this line, that is self-similar. Otherwise, non-self-similar. So importance over here is that in composites, you would rarely see a self-similar crack growth. They are non-self-similar. Again, a possible failure near the notch or hole, matrix cracking, matrix shearing, particularly in 45 layers due to high shearing stress along plus or minus 45, fiber kinking only for compression, delamination between layers. In fact, all these you can see in my previous pictures, these various failure modes mostly. They're all mixed, but this is we have shown. Okay. Notch strength analysis of composites. So notch resolution strength predictions, semi-empirical and FAM. In semi-empirical, we are trying to discuss now Whitney-Newsman point stress criteria, Marlin approach. Another approach is strength softening, which I'll not be discussing now because it's a bit complex and involved. I've deleted this. In fact, I had developed this approach for other predictions while I was at Boeing. R-curve methods, crack growth analysis. This also I'll not be presenting. I think the most important is these two approaches, and this is what I'll be discussing so that you get a feel how to determine the residual strengths. FEM, I would not be talking about the FEM methods, but in FEM, you would use VCCT, virtual crack closure technique, LAFM, linear elastic fracture mechanics, or cohesive zone modeling, continuous damage mechanics. I can send some references, some publications for those who are interested in pursuing this. It's a good area, in fact, damage tolerance, notch residual strength. In fact, you would find thousands of publications, people working for us 40 years, 50 years on the fracture mechanics of composites, fracture mechanics of metals. Okay, limitations of empirical approaches requires calibration of characteristic parameter from test data. They are called empirical because they are not based on pure theory. There is no way we can predict the failure using the equations from theory of elasticity. We use the equations from theory of elasticity for stress distribution and then consider the test data, come out with some kind of a empirical equations parameters. Characteristic parameters depend on material type, layups, we'll talk about it. And they do not address the characteristics of the crack tip damage zone. That's difficult. What kind of damage zone occurs? Whether it's a fiber split or damage delamination or matrix cracking, nothing of that sort. It just gives you the residual strength, which is calibrated using the test data. Crack tip damage zone is simulated as some effective notch tip damage zone. We'll discuss that. Damage assumed to grow in a self-similar manner. That is big assumption here. As I've shown the slides, which are saying, oh, there's hardly any self-similar crack growth. And we are using the assumption self-similar manner. The reason being, if we do not make this assumption, because what we are dealing with in our application here, we are not considering the propagation. And we are just considering the initiation. So going back to the slide, suppose, if we consider that the damages start initiating before it causes the propagation. And this is what we are trying to do. We are not considering the growth of the damage, how it's growing, in which direction. So we are ignoring that, and just the initiation we are considering at the ultimate load or whenever the failure occurs. That's it. Okay. Limited applicability to multi-directional loading because our analysis methods are limited to only unidirectional loading over here and not suitable for non-self-similar damage growth. If you want to consider this phenomena, what we are considering here, for non-self-similar, that is crack deviating from the path of the original crack, then these methods are not applicable. That is being predicted by using the FAM methods. There are lots of methods where the crack growth studies have been done in composites. Damage growth in composite, damage growth can occur by intrapolary damage or interlaminar damage. Intrapolary damage, that is within a ply, transverse matrix cracking, fiber microbuckling, fiber failure, fiber pullout. All these modes are being considered when people have modeled the damage growth in composite using finite element method. There are lots of methods available, but not the closed form solution, by the way, for any of this. Interlaminar damage, the delamination, and damage interaction coupling. Some like just pictorial presentations, so like fiber fracture, matrix transverse crack, delamination. Damage growth methods, laminate presented as homogeneous and isotrophic material, intraply damage, interlaminar damage, continuous damage mechanics, damage represented by reduction in corresponding stiffness. I won't go into the details of this. I just wrote just some points about damage growth methods and interlaminar damages, interface fraction modeling such as cohesive zone models and virtual crack closure. And these are being pursued a lot. In fact, tomorrow I'll send you some references about this and also these ones. So those who are interested in pursuing further studies, interesting area, or maybe PhDs can use it. Damage reduction coupling, okay, I won't go into. Now, notches or holes, residual strength evaluation. Holes first, I'm considering. Okay, now, the basis of point stress. One of the thing, in fact, there was a reference about one of the publications by Vadoops in the beginning, and I said I removed that work. I used to have those slides, and I thought it's getting too much. But what they did, before, in fact, Whitney and Newsman published their work, in 1971, Vadoops and their team at, I think they were at General Dynamics or I think they were General Dynamics. They studied some composites with the holes. So what they did, they loaded the hole of about, I think about 3 millimeter, 4 millimeter diameters in fatigue, loaded for about 1 million cycle. And then after loading that for about 1 million cycle at certain loading, they then loaded to the static because the failure had not occurred. So then they determined the residual strength after fatigue loading. And what they found, to their surprise, that the residual strength of the laminate with the hole after the fatigue cycling, that is almost 1 million cycle, the residual strength was higher than the residual strength of non-fatigue cycled coupons. That is, the coupons which were not cycled, they had a lesser residual strength or notch strength with the hole than the coupons which had been fatigue cycled. What is the reason? They found the reason was that after fatigue cycling, at smaller stress levels, the whole damage around the hole edge occurred. So a small damage developed, as I've shown in the qualitative pictures in my slides, which then led to the reduction in the stress constant factor and led to the increase in the residual strength. So that is the effect of the damage. So they had modeled based on that, and they called inherent zone modeling, and they used Bowie's corrective solution to determine the residual strength. Again, finally, the criteria is similar to this one. That's why I prefer this. And this is popular point stress criteria, which is also based on the same principle that near the notch or the hole tip, there's a damage zone developed when you are loading the coupon. And this damage is relieving the stress because the stress constant factor is reducing. So this is behaving like a plasticity, and that means this peak will drop, really. So the effect of this is the development of the point stress criteria by Whitney and Newsman, which is shown over here. So what we say from the point stress criteria is that there is some damage zone around the whole edge, and the failure would occur when at this distance, characteristic distance, we call this as a characteristic distance, the stress is equivalent to unnotched failure strength. Sigma naught is the laminate failure strength without hole or notch. So failure of laminate with hole occurs. Stress sigma y at d naught ahead of the hole reaches the unknown tensile strength of the material sigma naught. That is sigma y x equal to r plus d naught. Oh, this is error. This here, the comma should be here actually. And this should be sigma y equal to 0. So this should be deleted. Sigma should be deleted. Let me delete it here. Okay. So x equal to r plus d naught, y equal to 0. So sigma y is sigma naught. That is when the failure would occur. And d naught is point stress characteristic dimension. Now we had written down this expression sigma y upon sigma naught. This is the stress distribution. And so that means when the failure occurs when x is equal to r plus d naught. So if we substitute here, instead of x, r plus d naught, and solve this equation, that will give this equation, sigma n infinity. We are providing the infinity letter because for an infinite plate. And if it's a finite plate, in terms of the width of the plate compared to the hole, so the functionality of that, we call that finite width correction factor, which will apply. So this is for infinite plate, when the hole is small compared to the plate size, this is the expression for the residual strength, where eta is equal to r upon r plus d naught. D naught is the characteristic dimension, r is the radius of the hole. And for finite width plate, we apply this correction y1, which is correction factor. So sigma n Nost strength for the finite width plate is equal to 1 upon y1, sigma n infinity upon sigma naught, where, so final expression is this one, where y1 is a finite width correction factor, which we have taken, say, from Peterson or in any book. Okay. So this is the point stress criteria equation, which is very handy to determine the residual strength for the laminate to the hole. So there are two unknowns over here, as you can see. One is the sigma naught, which is unknown strength, depends upon the laminate type, layer, material. Then there is another parameter, eta, basically is function of d naught. So there are two parameters, sigma naught and d naught. And both of these parameters depend upon the material, and various other parameters are shown in the table, which are how you then characterize these parameters. You have to determine by test the value of sigma naught and d naught using the nost coupons and unnost coupons. So characteristic distances are determined by test. Determine the unnost strength, sigma naught of the test laminate, by testing unnost coupons. Determine the notch strength of the laminate segment for the whole size. So suppose this is a D diameter, so test this coupon. Determine the appropriate KT for the laminate. Using the ratios for the notch strength, calculate the characteristic dimension D naught for the test data. So this equation, if you know sigma n, you know sigma naught. So the only unknown over here is eta, which is a function of D naught. So you can calculate D naught using this equation. Okay, characteristic dimension denote may vary with the hole size and layups. So there could be variation, of course. It is function of the material, layup, environmental conditions, hole size. So you might have to generate some charts in order to cover your design space for various layups. Because in the design, when you're doing, you would be having various layups, various percentage 0-degree fibers, environments, the hole sizes. So you have to cover for all those parameters. So you would generate some charts of D naught as a function of percentage 0-degree fibers, the hole diameters, layup sequences, so on, whatever the parameters are, environment for the design. Just comparison of some data and the prediction, some test data prediction using the data from Dineshkumar, as you can see, from some layup 090 and 045 minus 4590, the test data and their predictions. As you can see here, is matching, but as the hole size increases, is deviating. That means for these predictions to match with the analysis, you might have to tweak the D naught value. So for this seems that D naught for these ones is higher than D naught for this one. So depending upon that's what one has to do, calibrate the D naught value with the hole radius, and that's what is shown here. So probably with the hole radius is varying. I've shown here just a graph using those equations for various characteristic dimensions like 0.51. There's no test data over here, of course, comparison. It is just the effect of the characteristic dimension. As the characteristic dimension increases, you can see the residual strength improves. So that means you just can't use one characteristic dimension. Suppose use very small characteristic like 0.5. That means you will be too conservative in your predictions. So unnecessarily you will be putting weight penalty to the structure. So one has to be cautious when you are trying to predict the residual strength, that the right value of characteristic dimension should be there. Now, what this is showing, so we are showing the notch sensitivity that the strength, predicted strength is dependent upon the notch type, notch size. What this is showing here, notch insensitive, that is, this distribution is shown as if like a metal, aluminum, suppose you have aluminum, where there's a generalized yielding occurring over here, say all, and then the failure strength will not be dependent upon a stress constant over here. There's no stress constant. That means material is yielded significantly and the failure would occur like a net section failure. So sigma n upon sigma naught is equal to 1 minus d by w, which is net section failure. High notch sensitive generally. And this will discuss the implications. So this, what I've shown here, this is highly notch sensitive, which is showing, if I remove this y, then you would recognize y is just a finite width correction factor. So forget about this one. Suppose sigma n by sigma naught equal to 1 upon kt, which is like isotopic material, suppose you have, and you want to predict the elastic residual strength without considering plasticity, then the strength would be 1 upon kT. So suppose it's 3, so 1 upon 3 would be the residual strength ratio. So that means this is highly not sensitive. Then somewhere in between, highly not sensitive, which can be predicted by this equation. That means the strength predicted by this equation would be somewhere in between this and this. So these are ultimates. This is for notch insensitive, this is for notch sensitive totally, and this is somewhere in between. This is what I've tried to show here, 3 types of distributions. Sensitivity, this is notch insensitive, which is simply this equation, that there is no effect of the notch size, notch. And here, what you see, this one is based on the point stress criteria, the residual strength, and this is based on purely stress concentration factor, 1 upon kT. Why you are finding this d by, because this is d by w effect as the panel width in comparison to as the hole is increasing in size compared to panel width, and this is the variation is coming due to the parameter y, which is the function of the finite width correction factor. If this is infinite panel, then what you will find, like this one here, where you have a very large panel, the hole is smaller. So from this graph, what you are seeing here, when the hole size is smaller, then the realistic estimate of the strength is predicted by this line, which is point stress criteria. But as the hole size is getting large, suppose this is 100 millimeter panel. So what you are seeing here, d by w, that means diameter is 40 millimeter. For say 40 millimeter crack, hole, the prediction using the point stress criteria and prediction using that notch sensitive criteria, 1 upon kT, is merging together. So what happened, the utility of this behavior is to show you that in this region, for the holes up to around 25 to 40 millimeters, almost 40 millimeters, we can use point stress criteria to predict the residual strength. But beyond that, for a larger hole, like beyond 40 millimeter, we don't worry about the point stress criteria. We just use this criteria to predict the notch, hole strength. I'm talking of notch, but it's a hole here. Notch will mean the cracks, sharp cracks. So this what simplifies here using this criteria, that for larger holes, we can straight away use the stress constant factor. And this is what we normally use when we want to predict the behavior. Large hole, we wouldn't worry about point stress criteria. We would just use the KT factor. But for smaller holes, point stress criteria, this one. That's why I was trying to show this chart. This is, I have taken, so this is just to validate this behavior in the next one, as you can see from the test data. This is the test data I have taken from Rhodes, Mikulas, and McGowan from NASA. Basically, this is NASA work. And as you can see, for a compression test panel they had done for certain layups, for T300-5208 material, I should have written the layup. I don't have not written, but I can put that in my revised slides. So you can see here, this is test data, and this is a point stress equation, which I have shown you earlier, with proper finite width correction factor applied. This is W equal 127 millimeter panel and with holes of different sizes. As you can see, how beautifully this test data is following the prediction using D naught equal to 0.5 millimeter. And this is the equation based on 1 upon KT. So what I said earlier, that for larger hole sizes, point stress criteria and the stress constraint approach, which is 1 upon KT approach, would predict the same behavior. And that's what you're seeing. So this is based on the test data. So test data really validates this hypothesis, which we are talking about. Effect of raising toughness on non-compressive strength quasi-isotropic. Now, I've just put some data for T300 BB9078, which is a toughened material. The fiber is same in both. This is brittle material and this is toughened material. And you see here for the quarter-inch hole, the hole is a quarter-inch hole, I think. I think it's a 6.4. I'll check up, but diameter of the hole is 6.4 millimeter quarter-inch, I think, if I'm not wrong. So failure stress 529 MPa and 726 failure strain, correctness dimension, and as you can see here, resin modulus 3.14. For this, I plotted from the test data of this Moisen. Again, this is from NASA. And this is for toughened one, SN by S naught. And this is for the brittle material.
Hello.
Hello, yes.
Sir, good afternoon. Sir, before applying the point stress criteria, each and every time we have to calculate the D naught value.
The thing is, when you are applying the point stress criteria, you need to calibrate your D naught from using the test data. So what happens, suppose in the design office, we are working and we want to predict the notch strength, the hole strength. We would have generated by test data various charts. As I said earlier, normally we'll dub the charts like that. D naught versus hole diameter for a particular material, and also as a percentage of 0-degree fibers for various layups. And that should be good enough. So once we have for that material these variations, based on this, then you can apply that for the same material with the relevant diameter and percentage 0-degree fibers. So you've already calibrated your D naught for particular material.
Yes, sir. So these are calibrated graphs. Okay.
Yes.
Okay. Yes. Yes.
I mean, this is
just
qualitative, but this is a type of behavior. We would do what happens. We will generate the equations. We'll always talk about the equations. Here I'm showing the graph, but if we are putting in Excel spreadsheet the equations, so we'll convert this in terms of the equations and put their behavior and determine. So we would have that. For laminate, we would have sigma naught, which is a notch strength. Again, based on the test for a particular laminate, we will correct this dimension. The moment we have these two parameters, we can predict the residual strength for the holes. And if you have a hole size greater than about 40 millimeter, as you said, then you don't need D naught. you just use this equation, KT.
Yes, notch sensitivity.
Yeah, 1 upon KT. As I've shown here, that in this region, then you don't need point stress. You can just use 1 upon KT. So
Right, sir,
suppose
got
KT is 3. So that means 1 upon 3, that is sigma naught by 3, is your residual strength for the whole. Simple.
Thank you, sir.
And this works well. And that's why I've just put some data to validate this to show you the utility of this method. And most of the time, I would use point stress criteria in the industry. And I've used point stress quite often for predicting the residual strengths. So it's an important method. Let me tell you that for an industry, it's an important method. It's a simple, but very useful. This behavior is very useful. Point stress over here, KT over here. I think what I can do, I'll be talking about the cracks. I can stop here and invite some questions rather than continuing. So you can ask the questions. Any doubts, any questions so far on this?
So can you show the formula for point stress method in the slide which you have?
Okay, yes, let me just show you. Yeah, this one.
Yep. Okay. No, yes. So this method point stress can be method can be applied for both composites and for metals, right?
No, metals, we don't use this method. No.
Oh, okay. So only for composites we have to
Yes.
use point stress method. Okay.
That's right.
And for the metals, it doesn't matter how much. What is the size of the hole? We always use.
Well, in metals, what happens? Because the yielding, normally, because if you're determining the strength of the ultimate load, you just use the net section stress, assuming that the material will yield
Yes.
aluminum. And if it's a brittle material, you just use KT, 1 upon KT. If there is no yielding, then the failure would occur with 1 upon KT straight away.
Yes, sir.
In metals also. If it's a brittle material, metal, because the utility of this one, point stress, why it's working, I said, because we are assuming this damage zone, which is relieving the stress constant factor. If there is no relief, assuming there is a zero, this one, that means the characteristic dimension is 0. And if it is 0, that means the stress over here at this point, when it approaches the unknown strength, the failure would occur. So it's very simple. Based on this stress distribution relationship and the damages. Now you would ask, for large hole, why is KT? Explanation I had written down here. In fact, hole diameter effect on residual strength. So in previous slide I had shown, and this mechanism I'm trying to discuss now, that you see for a 40 millimeter hole, the stress distribution from the edge of the hole is this one. Most of the region is under high stress. For a smaller hole, this is a rapid drop. So suppose we consider, okay, there is a damage zone, which is like D0, and our criteria for the failure is when the stress at this point reaches the unnosed strength. So that means, and we consider, okay, assuming D0 to be the same for large and small one, okay. There could be a small difference, but assuming the same. And that means the failure of this one would occur when at this point the stress reaches the unnosed strength. So you see in this equation I've tried to show the inequality and equality. That means SY1 upon SG is gross stress applied, is less than SY2 upon SG, as you can see from this figure. So failure occurs when SY1, the stress here and here is equal to S0. If the failure occurs when this is equal to S0, therefore, using this inequality, failure gross stresses are then S0 upon SG1 less than S0 upon SG2. That means SG1 is greater than SG2. So what you see here, the failure stress for this one, a small hole, is larger compared to the larger hole based on this stress distribution phenomena, the effect of the hole size. So all the time I discuss the hole size effect over there in these graphs. You can see when hole is increasing in size, your residual strength is coming down, which is based on this fact also you can argue as the hole size increases, the residual strength is decreasing. Any question? Any more question?
Excuse me, sir.
Yes, sure.
Sir, I am Pradeep here.
Yeah.
Sir, may I know actually this D0, that is material dependent?
Yes, it is.
And it depends on the volume fraction of the fiber and matrix?
Yes, it will depend on many parameters and it's very difficult actually. Yeah. So what happens, you test a few different types of laminates.
Okay.
And then generate some kind of a curve functionality. So in fact, I wrote here the characteristic dimension is a function of various parameters. Where did I put here? Might have removed it, but I think I removed that. I put here the characteristic dimension function of. Yeah, I think I removed it. It used to be there. Various parameters. That's surprising. I think while tweaking my slides, I might have removed some of the slides. Let me see. Compression. Oh. Hole damage here, parametrics. Parameters affecting. So all these parameters do affect the notch strength, which is a function of various characteristic dimensions. But I'll make them clear in this presentation. But yes, it depends.
Sir, is there any empirical relation to find the determine D, or it is obtained both from the test and analysis.
Test and analysis. What happened, actually, C.C. Christopher Poe, he tried to determine based on the test using this graph. Let me just go back to using this damage zone and classify it probably approximately, but it is difficult. How much is the damage zone D naught value from here? It's extremely difficult. So there's no way. It's only the best way is test the notched laminate and unnotched laminate, and using the equation predict the characteristic dimension. And that is the standard way we always do that.
Okay.
Rather than using the equation, some people might use the finite element method to predict that. But I found rather than using finite element method, using unnecessary complications, I would use these equations which are simple and give the same result as finite element. I myself tested that. So
suppose it is laminate, sir. So which lamina we need to consider to determine the characteristic distance?
You have to use the laminate, not lamina. Your laminate.
Because laminate means that a different plies stress level will be different, na, sir?
Don't worry about it. You are talking about the gross stress. Laminate stress, not the lamina stress. So
average stress.
Yes, average stress. So suppose you are testing a laminate with a 10 plies, 20 ply, 15 ply, depending upon the layups, load it and determine the failure load. And then you have unnotched strength. Using the equations which I have shown in this, those equations calculate. So simply like a 10 ply, 20 ply, 15 ply, depending upon your design layups, you would test for various laminates and generate the data sufficient for your design space.
Sir, this is valid for both static as well as fatigue?
No, fatigue is totally different phenomena.
Fatigue.
I'll talk about it later on.
Okay.
And this is why I said, you can't predict damage propagation. And I made it very clear, we are just predicting initiation, not propagation yet at all. It's extremely difficult to predict the propagation. And there are a lot of models which I've said in my slide here, CDM, damage growth in composites. And I'll send you some references. In fact, there's a lot of interesting work.
Sir, references, if it is possible, sir, we can understand better, sir, if you can share.
Oh, I'll send the papers tomorrow. I intended to send today, I could not, but I've got heaps of papers. There's no problem. They're all finite element method based and quite complex. And generally what happens with these methods, which I'll be talking later on, of course, next week. Using the finite element method, the methods, because complex loading is there, then you can't use these equations. Impossible. You will generate the effect of various parameters using finite element method, validate the finite element method with the test data using some coupons, element test, or panels, and generate some kind of a surface parametric analysis to do using some linear programming. There is standard programs available. And then using those programs, you will generate some kind of a empirical equations. And that is what is used by the industry. Empirical equations developed using finite element method, test data to analyze the structures. There's no way you can test every structural feature. And that is why there's always importance of developing some kind of empirical methods, because there's nothing exact about it. Empirical methods based on finite element, analytical and test data, and generate some parametric study, and generate equations. And that's how the predictions are done. So I'll send you some references, surely.
So this is essentially, sir, you are talking about the static failure.
Only static, yes.
Okay.
Under fatigue. Fatigue is very complex, and you can't predict the behavior. In composites, normally we use the no growth phenomena. In metals, we use the growth because you can predict the crack growth by dA by dN equal to C delta Kn delta by Paris law. In composites, except the delamination, there's no way through thickness crack damage propagation you can predict easily. A lot of work has been done, but there's no method available which can predict the fatigue behavior. And that's why in composites, we do not use the damage propagation at all in the fatigue. We design it based on the no propagation, no damage growth. That is the criteria in composite, which I talked in my certification.
Yes, sir.
And I'll be talking about it next week, about the damage tolerance and durability approach, which would be very useful.
But sir, delamination growth is also a kind of propagation, just as in metal, sir.
Delamination, it is propagation in composites like a metal, of course, crack, which people have tried to correlate using a dA by dN as a function of a stress and factor or strain energy release rate, similar
Yes,
to
sir.
metal.
Yes, sir.
However, my experience has been that in composite, the delamination jump occurs quite often under load. Suddenly it jumps the crack, and that phenomena changes the behavior. In metals, the crack doesn't jump. It always grows slowly.
Okay, sir. For this, sir, any reference, sir, we have, sir, in open literature, sir?
Which one?
This delamination growth, that regarding that, sir?
Yeah,
We'll be having
delamination growth, many people have done, and I'll send you some reference. I'll see if I got the hard copy. I won't have soft. I'll see what I have. But I'll send you some references shortly about the delamination, where
just to know that, sir, this we cannot use in the aircraft industries. Delamination growth. Normally, the usual method is the only without considering the delamination growth, only as an approach. Only to refer to have a reference on that.
That's a complex phenomena. There are methods available for delamination growth has been considered in some cases, but I would like to have a caution on that. It is not for proof. Sometimes the crack could jump the delamination, but yes, delamination theories have been developed in order to predict the delamination growth similar to the metals.
But that period is very slow. Very quickly it happens delamination. So we don't consider that period, that time. That is the reason, sir. It jumps, it goes very fast. So that it is as good as not considering that. Is that the reason, sir?
The problem is really to come out with a reliable prediction of the delamination growth. And currently, we don't use it in practice. I can discuss the criteria for certification. The delamination, we don't use as a rate of delamination propagation and work out like in metals, we develop the inspection plan. You see, the purpose of
Yes.
crack growth rate prediction in the metallic structure is to develop the inspection intervals for maintenance and to understand when the crack will grow and reduce the residual strength of the structure below the regulatory requirement, which is usually the limit load. In composites, we use a different phenomena to cover delamination. We would say if the delamination is there, then it can grow to length, say L, like 100 millimeter, 200, 300, 400 millimeter before it will cause the residual strength to be reduced below the limit load carrying capability. And that growth, we should be able to determine during the inspection interval. That means we have to consider that much of delamination, if it is growing, it should be prevented by some like they call chicken fasteners, say. So we have to consider right at the design stage, the presence of that much of delamination and carrying the limit load capability. And that is the criteria.
Sir, normally we consider the critical strain energy release rate.
Yes.
So that is one. And again, you said that, sir, limit load also. So what we should consider are both together?
No. Look, limit load, when we are saying that is the capability of the structure to carry the limit load, but then you are
static load, yes.
Then you are calculating for that limit load the strain energy release rate. That's a different thing. So you are applying that load in order to calculate the strain energy release rate, and when it becomes critical.
Yes.
Okay. So then the fracture would occur. So that will be the residual strength prediction based on the critical strain energy release rate.
Yes. Both happens together, sir.
Yes, it's a criteria.
At the same location, yes. Critical, we are essentially deriving the limit load out of the critical strain energy release rate.
Yes, the thing is limit load is prescribed because you are designing the aircraft structure with the capability of handling the limit load. Now, at that limit load, what is your critical strain energy release rate for that amount of delamination? So it does not propagate. Okay, that's one thing. Another thing is you got to have, suppose you are saying that 200 millimeter long delamination is permitted. You have to demonstrate that the delamination will not propagate under any circumstances beyond 200 millimeters. That means you got to have some crack arresters.
Yes.
So calculating the critical strain release rate is not sufficient enough. You got to arrest a crack.
Correct.
By having some kind of chicken fastener or other mechanism, so that crack does not propagate or delamination does not propagate beyond that. Any more questions?
All right. Thank you, sir.
Anyone else? Any question? Okay, if there are no questions, I'll see you next Thursday a week after today. That means 21st of October, the same time. And good night.
Good night,
Good night,
Dr. Gar. Thank you very much. See
Thank
you
you,
next
sir.
Thursday.
Good night, sir. To all.